What does the word geometry actually mean? Most of us learned it in school, angles, triangles, proofs, but few of us ever stopped to ask where the word itself comes from. Geometry, from the Greek, geo, meaning earth, and metria, meaning measurement. Geometry literally means earth measurement. This isn't a coincidence. The ancient Greeks, Euclid, Pythagoras, Thales, they didn't invent geometry in the abstract. They discovered it by measuring actual land, real soil, real distances. They were surveyors, dividing fields, constructing buildings, mapping territories. And from those measurements of the earth beneath their feet, they derived the principles we now call Euclidean geometry. But here's what's fascinating, and perhaps a bit puzzling. If geometry means measuring the earth, and Euclidean geometry came from measuring the earth, why are we told that earth itself doesn't actually follow Euclidean geometry? Welcome to Chapter 1 of Parallel Gravity by Daskalos Cleary, Geometry and Measurement. In this chapter, we're going to do something simple, yet radical. We're going to take measurement seriously. We're going to look at what happens when we use levels, plumb bobs, and surveying equipment to actually measure the earth. And we're going to ask whether those measurements might be telling us something important, something we've been trained to overlook. Let's begin. Chapter 1, Geometry and Measurement, the word itself. Before examining any evidence about Earth's shape, we must understand what the word geometry means. It comes from Greek geo plus metria. Geometry literally means earth measurement. This is not coincidental. Ancient mathematicians Euclid, Pythagoras, Thales developed geometry by measuring actual land. Surveyors divided fields, constructed buildings, and charted territories. They measured the earth beneath their feet, and from those measurements derived the principles we call Euclidean geometry. Here's the puzzle. If geometry means measuring the earth, and Euclidean geometry emerged from measuring the earth, why are we told that earth itself doesn't follow Euclidean geometry? Euclidean principles. Euclidean geometry rests on several basic principles. 1. Parallel lines never meet. 2. Parallel lines remain equidistant forever. 2. Triangle angles sum to 180 degrees, always without exception. 3. Vertical lines are parallel. Every plumb line hangs in the same direction. 4. Horizontal means perpendicular to all verticals. A level surface is perpendicular to every vertical line, not just one. 5. Space is uniform. Three-dimensional space extends consistently in all directions. These weren't invented arbitrarily. They were discovered through direct measurement. For over 2,000 years, every surveyor, builder, and engineer has operated according to these principles, and they work. The vertical question: consider the simplest surveying tool, a plumb bob, a weight on a string. Gravity pulls it downward, defining vertical. Now ask, are all plumb lines parallel to each other? According to Euclidean geometry, according to practical construction, the answer is yes. A plumb line in New York points in the same direction as one in Los Angeles. Any two vertical lines extended infinitely remain equidistant and never meet. But according to the standard spherical model, this is wrong. Plumb lines supposedly point toward Earth's center. A plumb line in New York and one in Los Angeles would converge, meeting roughly 3,959 miles below the surface. Which is it? Are any two vertical lines parallel to each other, or do they converge toward a center? Every construction project assumes they're parallel. No engineer accounts for convergence when designing a building or bridge. No surveyor adjusts for it when establishing baselines. Why? Because at every measurable scale, any two vertical lines are parallel to each other. This, the horizontal plane. What does horizontal mean? What makes a surface level? In Euclidean geometry, a horizontal plane is perpendicular to gravity, perpendicular to the vertical direction. If you place a level on the ground, the bubble centers when the surface is truly horizontal. That surface is the same everywhere. A level plane in New York is parallel to a level plane in Los Angeles. The standard model claims this is an illusion. Level doesn't mean a plane, it means following Earth's curve. When you build a level foundation, you're supposedly conforming to a spherical surface with radius 3,959 miles. Yet no builder measures this. Foundations are checked with lasers, transits, and levels. They are made level, genuinely perpendicular to gravity across their entire extent, not tangent to a local sphere, but horizontal planes. Over hundreds of feet, over miles, surveyors establish level reference surfaces. City grids are laid out on planes. Baselines for mapping are horizontal. Rail lines are built level. If Earth were spherical, these surfaces should show measurable curvature. They don't. Large-scale measurement. The most compelling evidence comes from historical surveying. Before satellites, before GPS, surveyors mapped entire continents using ground-based measurements. They used theodolites, chains, and levels. They established baselines, long, straight, horizontal reference lines, and built triangulation networks from them. These surveys were accurate to within inches over hundreds of miles. The U.S. Coast and Geodetic Survey mapped the United States this way. Transcontinental railways were built using these methods. All assumed Euclidean geometry over the distances measured. Did surveyors account for Earth's curvature? Officially, modern accounts claim they did. But examination of historical records shows baselines were physically measured as straight, horizontal lines. The geometry used was Euclidean, and it worked perfectly. If Earth truly curves at the standard rate, then over 100 miles there should be a deviation of over 6,600 feet, more than a mile. Yet surveyors established level baselines over such distances without encountering these problems. The convenient answer. When confronted with this evidence, the standard response is, Earth is effectively Euclidean locally. Over small distances, they say, Earth appears to have Euclidean geometry. It's a good approximation. But what is local? A few feet, a mile, 10 miles, 100? The definition shifts. Salt pans spanning 31 miles with no measurable deviation from horizontal. Still local. Continental surveys using Euclidean triangulation. Local approximations. At what point does local end and global curvature begin? The answer is never clearly defined. It's conveniently vague, expanding to accommodate whatever observation is being discussed. This isn't science. This is rationalization. What measurement reveals return to first principles. Geometry means measuring Earth. When we measure Earth directly, we find vertical lines remain parallel over all tested distances. Horizontal surfaces extend as planes over vast areas. Large-scale surveys use Euclidean geometry. Water finds level and maintains level surfaces. Construction assumes parallel verticals and horizontal planes. These methods work flawlessly if Euclidean geometry emerges from measuring Earth. Perhaps Earth is Euclidean. Perhaps geometry truly describes Earth measurement, and the measurements speak clearly. The presupposition problem. Here's the deeper issue. The claim that Earth is spherical is not derived from direct measurement. It's a presupposition that shapes how measurements are interpreted. When a surveyor uses a level, does the instrument reveal curvature? No. The surveyor assumes curvature exists beyond measurement range and interprets accordingly. When water sits level across a 31-mile salt pan, does it show a curve? No. We're told the surface is curved, but our instruments can't detect it because they follow the curve. This is unfalsifiable. There is curvature, but no instrument can measure it directly. Compare this to Euclidean geometry, which makes testable predictions. Vertical lines are parallel and perpendicular to all horizontal planes. These can be tested, and when tested, they hold true. Which approach is scientific? The one making testable predictions, confirmed by measurement, or the one claiming undetectable effects that must be accepted on faith? The circle of interpretation. The standard model uses circular reasoning. Claim Earth is spherical with a center. Evidence. Gravity pulls toward Earth's center, causing verticals to converge. How do we know gravity pulls toward a center? Because objects fall downward, interpreted as toward a center. Why interpret it that way? Because Earth is spherical with a center. The circle is complete. Earth's shape justifies the interpretation of gravity, and gravity justifies Earth's shape. There's no independent verification. We never directly measure convergence of verticals. We never directly observe curved horizontal surfaces. We simply assume they exist because our framework requires them. Breaking free, To break this circle, examine observations without presuppositions. What do we observe? Objects fall straight down. Plumb bobs hang parallel. Water surfaces are level planes. Surveys use Euclidean geometry successfully. What does this require? Gravity acts uniformly downward. Spacious Euclidean vertical lines are truly parallel. Horizontal surfaces are truly planes. Does this require a spherical Earth? No. Does this require convergence toward a center? No. Does this require curvature of surfaces? No. The simplest interpretation, the one that takes observations at face value, is that Earth's geometry is Euclidean. Vertical lines are parallel because gravity acts uniformly. Horizontal surfaces are planes because they are perpendicular to uniform gravity. The center is an unnecessary assumption inherited from ancient philosophy, specifically Aristotle, as we'll discuss in Chapter 10 in another video. Practical success, consider this. Every practical application of geometry assumes Euclidean principles. Surveying establishes horizontal baselines and parallel verticals. Construction builds structures assuming parallel columns and level floors. Engineering calculates stresses and forces using Euclidean geometry. Navigation uses coordinate systems based on planes. Manufacturing produces components to Euclidean specifications. All of this works. Buildings stand, bridges span. Surveys are accurate, parts fit together. If Earth's geometry were actually non-Euclidean, if verticals converged and surfaces curved, then these practices should fail or accumulate errors. They don't. Classical Euclidean geometry works because it accurately describes Earth's actual geometry. The measurement standard science should be empirical, based on what can be observed and measured. When we measure Earth, we find parallel verticals. We find level horizontal surfaces. We find Euclidean triangulation works over continental scales. We find no measurable convergence or curvature. These are direct observations. The claim that Earth curves despite these observations requires either 1. Declaring the measurements invalid, or 2. Claiming the curvature exists but is somehow unmeasurable. Neither option is satisfactory. The scientific approach is to accept what measurement reveals. Earth's geometry is Euclidean. The implications: if Earth's surface geometry is Euclidean over all measurable scales, several implications follow. For physics, classical mechanics is exact, not approximate. Newton's laws work perfectly because they describe a truly Euclidean reference frame. For cosmology, the relationship between terrestrial observations and celestial mechanics requires re-examination. Gravity on Earth's surface may operate differently than gravitational interactions in the heavens. For epistemology, direct observation and measurement are more reliable than theoretical frameworks imposed from above. These implications are significant, but they follow naturally from taking measurements seriously, from trusting what geometry actually reveals. Conclusion: trust the measurement. The word geometry tells us what it is, measuring the Earth. When we measure Earth using levels, plumb bobs, transits, and lasers, we consistently find Euclidean geometry. We find parallel vertical lines, horizontal planes, triangles with 180-degree angle sums, straight lines as shortest distances, uniform three-dimensional space. Perhaps we should trust these measurements. Perhaps geometry, Earth measurement, reveals truth. Earth's surface exhibits Euclidean geometry at all tested scales. In the next chapter, we'll examine what happens when we apply these principles to water, the most honest substance in nature. Water doesn't lie. It responds directly to gravity, finding equilibrium on level surfaces. What does water reveal about Earth's geometry? The answer is both simple and profound. Geometry equals measure. When we measure Earth, we find Euclidean geometry. Perhaps Earth is Euclidean 3 space.